Hi there, my name is Tara Vohs, and today I'm going to show you guys how to solve problem 4.14 in the 6th edition of Principles of Polymer Systems by Ferdinand Rodriguez. Let's take a look at the problem. The decomposition of benzoyl peroxide is characterized by a half-life of 50 hours at 60 degrees Celsius and an activation energy of 27.3 kilocalories per mole. How much peroxide, in moles per liter, is needed to convert 1/3 of the original charge of vinyl monomer, original concentration 2 moles per liter, to polymer in 85 minutes at 70 degrees Celsius. Okay, so the first thing we're going to do is list out our given information. We are working with two conditions here. The first condition is at a temperature of 60 degrees Celsius, or 333.15 Kelvin. Here, the half-life of our initiator, benzoyl peroxide, is 50 hours. The second condition is at a temperature of 70 degrees Celsius, or 343.15 Kelvin. A reaction takes place at this condition for 85 minutes. In this reaction, 1/3 of the original monomer concentration is converted to polymer, and the original monomer concentration is 2 moles per liter. The quantity that we're trying to find is the concentration of initiator used in this reaction. We also have two pieces of data that hold for both conditions. The first is that the energy of activation of the initiator is 27.3 kilocalories per mole, or 27,300 calories per mole. The second is that the quantity Kp squared over Kt is 128 liters per mole hour. Okay, next we're going to look at the equations we're going to be using to solve this problem. The first thing we need to do is find Ki. To do that, we're going to use equation 4.9 and 4.10. Then, once we have Ki, we can plug it into equation 4.6 in order to find the initiator concentration. Equation 4.6 is a simpler form of equation 4.13, and it assumes that the initiator concentration does not change throughout the reaction. Since our initiator has a half-life of 50 hours at 333.15 Kelvin, and the reaction only runs for 85 minutes, we can assume that a negligible amount of initiator will be consumed at that time. All right, now let's get to the solution. For part 1, we need to find the value of Ki. We're going to work under the first set of conditions first, so 333.15 Kelvin. At this temperature, we know the half-life of the initiator, so we can plug that into equation 4.9 to find Ki, which is 0.01386 hours to the negative 1. Rate constants are temperature dependent, so this is not going to be the correct value of Ki at 343.15 K. But the Arrhenius constant A in equation 4.10 is not temperature dependent, so we're going to solve for that first. So if we plug in the Ki value we just found, the activation energy in calories, and the temperature of 333.15 Kelvin, we're going to find A to be 1.128 times 10 to the 16 hours negative 1 moles negative 1. As a side note, the version of the gas constant R we're using here is 1.987 calories per Kelvin. Now all that's left to do is plug in our values for the second temperature conditions, 343.15 Kelvin. We just found the value of A, that stays the same. EA is still 27,300 calories. R is still 1.987 calories per Kelvin, and T is now 343.15 Kelvin. And when you solve that for Ki, you get a value of 0.0461 hours to the negative 1. Okay, now we can use that value in equation 4.6 to solve for the concentration of I. Before we do that, we're going to need to rearrange the equation a little bit. We're given the quantity Kp squared over Kt, so we want to write the equation in terms of that. Kp can be written as Kp squared to the 1/2 and put inside the parentheses there, while Ki to the 1/2 can be taken out. So what you're left with is this right here, which you can see is in terms of Kp squared over Kt. Now, equation 4.6 uses the initial and final concentrations of the monomer. We already know that the initial monomer concentration is 2 moles per liter, and we know that 1/3 of that gets converted. So to find the final monomer concentration, we can just do 2 moles per liter minus 2 moles per liter times 1/3. And what we're left with there is 1.33 moles per liter. All right, now we have all our values, so we can just start plugging things in. We just found both monomer concentrations. Kp squared over Kt is 128 liters per mole hour. Ki is 0.0461 hours to the negative 1. And the time is 85 minutes, but we're going to divide that by 60 to convert it to hours and keep the units consistent. After that, all you have to do is solve for the concentration of the initiator, which turns out to be 0.014 moles per liter. Thank you for watching, and good luck in class.